Today we are going to see Unit 11 P block elements. P block elements. Now you know that the elements of group number 13 to 18 are called P block elements. And why are they called P block elements? Because the last electron enters into the p orbital. Now in this chapter we will be studying about the properties of group number 13 and group number 14. Now let us see what are the reasons for the anomalous properties of first member of each group in P block. And we know that the first element of each group will show anomalous behavior in their properties, and the reason for this anomalous behavior is due to small size, high electronegativity, high ionization enthalpy. Their maximum covalency is 4. We know that the first element, they are in the second period of the periodic table, they have vacant d orbital. So the only orbitals available for these elements are s, 1s and 3 p orbitals. So total there are 4 orbitals available for bonding. So they can show maximum covalency 4 due to the absence of d orbital. And also these elements are able to form p pi multiple bonds. Now let us study this chapter in the form of question answer type. Now the question is, what do you understand by the term covalency? Covalency. Covalency is the number of orbitals available for bonding in the valence shell, and we discussed that the first element of each group can have maximum covalency 4 because they have only 4 orbitals available for bonding. Now the second period elements are the elements, the first element of each group. The second period elements has a tendency to form p pi multiple bonds. We know that the pi bond is formed by p orbital. So the first element can form p pi multiple bond, and the answer or reason for this is due to small size and unavailability of vacant d orbital. The first member can easily form p pi multiple bond. Now next let us see the general electronic configuration of this P block elements. The general electronic configuration. General electronic configuration is noble gas, NS2, NP 1 to 6. Now for group 13 elements, the general configuration is NS2 NP1, group 14 NS2 NP2, group 15 NS2 NP3, and with group 18 we have the NS2 NP orbital getting completely filled, that is the configuration will be NS2 NP6. The p orbital gets completely filled with group 18. Now let us study in detail about group 13 elements first. So group 13 elements. Now the elements of group 13, they are also called boron family. Boron is the first element in group 13. Now the elements of group 13 are boron, aluminium, gallium, indium, and the last element is thallium. Now the symbol is boron B, aluminium Al, gallium Ga, indium In, and thallium is Tl, is thallium. Now boron is in second period. Then aluminium third, 4, 5 and 6th period we have the element thallium. Now we know that the number of valence electrons number of valence electrons of group 13 element is equal to 3, and they can show the valency also equal to 3. And let's write the electronic configuration of group 13 elements, and the general E dot C of group 13 is noble gas, NS2 NP1. So you can see that the total number of electrons, valence electron is 2 plus 1, which is equal to 3. So they can show a valency 3. Now let's try the electronic configuration of these elements, that is from boron to thallium. The general configuration is NS2 NP1. Now let's try the electronic configuration. Boron configuration is, boron takes the configuration of noble gas helium. So let's try the noble gases first. Helium, neon, argon, krypton, xenon. These are the noble gases. Now let's try the outer electronic configuration. We know that boron is in second period. So the N value will be equal to 2. So the configuration will be, outer configuration will be 2s2 2p1, here 3s2 3p1, 4s2 4p1, 5s2 5p1, and 6s2 6p1. So this is the outer electronic configuration of group 13 elements. Now we know that boron has no d orbital. It is not present in boron, whereas aluminium, aluminium is in third period, 3d orbital is present but it is vacant. Now the gallium has 3d orbital filled but 4d orbital is vacant. Now indium has 3d and 4d orbital filled but 5d orbital is vacant, and thallium 3d, 4d and 5d orbitals are filled, whereas 6d orbital is vacant. And in thallium we have 4f orbital also getting filled. So the boron no d orbital, whereas aluminium 3d orbital is present but it is vacant, and the filling of 3d orbital starts in gallium, that is in the fourth period element. Now let us discuss few questions based on group 13 elements. The first question is, boron forms only BF4 minus, while aluminium can form AlF6 minus. Now you can see BF4 means there are 4 bonds formed with fluorine atom and boron, whereas AlF6 means 6 bonds are formed between aluminium and fluorine. Now the answer is, boron can exhibit maximum covalency of 4 because only 4 orbitals are available for bond formation and they don't have the d orbitals in them, whereas aluminium, we know that aluminium has vacant d orbital which can be used for bonding. Now next question, write the isotopes of boron. Now there are 2 isotopes for boron, and the isotopes of boron are, isotope means atoms of same element with same atomic number but different mass number, and atomic number of boron is 5. Now one isotope is boron 10 and the second one is boron 11 with atomic number 5. Same atomic number but the mass numbers are different, one is 10 and one is 11. Now next question, atomic radius of group 13 elements are smaller than group 2. Why? We know that group 13 comes after group 2, then after 2, 3 to 12 are the transition elements, then we have group 13 element, and we know across the period the atomic radius decreases. And what is the reason? Across the period the atomic number increases but nuclear charge increases. Also, what happens when nuclear charge increases and the electrons are added to the same shell? Nuclear charge increases, Z effective increases, so atomic radius decreases. Now next question is atomic radius of gallium. Gallium is Ga. Gallium is 135 picometer, is slightly lower than aluminium. Aluminium is 143 picometer. 1. Now we know that this boron, aluminium, gallium, that is the order of the elements, boron, aluminium, gallium, and we know that down the group size increases. So according to the trend that we have studied, gallium should have bigger atomic radii than aluminium, but here the question is the atomic radius of gallium is lower than aluminium. Now what is the reason for that? Because in gallium we can say that there are 10 electrons in the 3d orbital. We know that with gallium the 3d orbital is filled, whereas aluminium has vacant 3d orbital. So in gallium there are 10 electrons in the 3d orbital, but due to poor shielding effect of d orbital, Z effective is more and the valence electron experience more force of attraction by the nucleus in gallium than in aluminium. So we know that as Z effective increases, the atomic radius decreases. Therefore atomic radius of gallium is less than aluminium. So in gallium there is screening effect. As a result of screening effect by d electrons, the Z effective is more, and so atomic radius decreases for gallium. Now next question is the ionization enthalpy. The first ionization enthalpy of gallium is slightly higher than aluminium. Why? We know that gallium has a small atomic radius compared to aluminium. So as the atomic radius decreases, ionization enthalpy increases. So the first ionization enthalpy of gallium is higher than that of aluminium. Now next let us discuss about the oxidation states. So next is oxidation state. Oxidation state. Now the common oxidation state. Now the p block elements can exhibit two oxidation states, and the two oxidation states differ by a unit of 2. Now you know that the general electronic configuration of these elements is noble gas NS2 NP1. So they can show two oxidation state, and the common oxidation states are +1 and +3. I told you the two oxidation states differ by unit of 2. So the two oxidation states exhibited by group 13 elements are +1 and +3. Now next point is down the group, which oxidation state is more stable? Now this is a very important point. Down the group, let it be any group in p block. Down the group, the stability of lower oxidation state increases and higher oxidation state decreases. So this point is very, very important. Down the group, lower oxidation state is stable, that is +1 is stable and +3 is unstable, which means +3 is stable for the first elements. Okay, so down the group, stability of lower oxidation state, in this +1 is the lower oxidation state, lower oxidation state increases and higher oxidation state decreases. Now what is the reason for this variation in oxidation state? And the answer is, this is due to a term called inert pair effect. So the reason for the stability of lower oxidation state down the group and the instability of higher oxidation state down the group is due to inert pair effect. Now let us see what do you mean by the term inert pair effect. The reluctance of S electron. S electron means the electron present in S orbital. The reluctance of s electron to participate in chemical reaction is called inert pair effect, and these inert electrons are called non-bonding electrons. Now, what is the reason for the reluctance of this s electron to participate in chemical reaction? The reason is due to poor shielding of d and f electrons, z effective increases. We know that down the group the d and f orbitals also gets filled, and due to poor shielding of d and f electrons, the z effective of the last elements in a group are also called heavier members or heavier elements or heavier members or higher members. So, Z effective of higher members, that is the last element of each group, increases. So, we know that when Z effective increases, electrons in s orbital are more tightly held by the nucleus and they remain as inert pair or non-bonding electron. So, this is the reason for the inert pair effect. Due to poor shielding of d and f electron, Z effective increases. So, the electron in s orbital are more tightly held by the nucleus and they remain as inert electron or non-bonding electron. Now, next we have a question. In thallium, we know the symbol of thallium is Tl. In thallium, +1 oxidation state is more predominant or is more stable than +3. Why? Or we have another question, thallic compounds. Thallic compounds means +3 oxidation state. Thallium is in +3 oxidation state, are less stable than Thallus compounds. Thallus compounds means they are in +1 oxidation state. Or we have another question, the answer for all the three questions are the same. The next question is, or TLOH is known but TLOH thrice is unstable. Why? Now, TLOH means we know the OH charge is -1, so thallium will take +1 oxidation state, and TLOH thrice means OH is -1, -1 into 3 is -3, so thallium takes +3 oxidation state. Now, if you look at the three questions, this is first question, second question, and this is our third question. In these questions, you can see +1 oxidation state of thallium is more stable, and we know the reason for that, because thallium is stable in +1 oxidation state because of inert pair effect. Now, the next question is BCl3. Next question, BCl3 is more stable than TlCl3. Now, if you look at the oxidation state, boron, chlorine charge is -1, -1 into 3 is -3, boron takes +3. Now, thallium chloride, then chlorine is -1, so the charge of thallium will be +3, -1 into 3 -3, so thallium takes +3. Now, the question is BCl3 is more stable than TlCl3. Now, you know boron is the first element of group 13, it is stable to higher oxidation state which is +3, whereas thallium is the last element of group 13, it is stable to +1 oxidation state due to inert pair effect. So, that is the reason. Now, next question, what are electron deficient species or compounds? Electron deficient species. Or there is another question, why are they called Lewis acids? Okay, so what are electron deficient species, and we can call these electron deficient species as Lewis acids. Why? Now, electron deficient species means the species in which the central atom does not have 8 electron in the valence shell are known as electron deficient compounds. Example for electron deficient compound is, example for this electron deficient species is aluminium chloride, BCl3. You can see that aluminum, around aluminum and boron, we have only 6 electrons. The octet is incomplete. So, they are electron deficient compounds. And why are they called Lewis acid? Lewis acid means, Lewis acids are electron pair acceptors, means they accept electron pair. So, you know that aluminum chloride and BCl3, they are electron deficient species. So, they accept electron pairs. So, they can also be called as Lewis acids. Now, next question is, down the group, tendency to behave as Lewis acid decreases. Why? Now, the answer is, down the group, you know, the size of the atom increases. So, larger the size of the atom, less is the tendency to accept electron. So, the tendency to behave as Lewis acid decreases down the group. Now, next question, why aluminum chloride exists as a dimer? Very important question. The question is, aluminum chloride exists as dimer. Dimer means 2 molecules of AlCl3, or the question can be asked as, how does aluminum chloride attain stability? We know that aluminum chloride is an electron deficient species. So, it is unstable. So, how does it get stability? By forming a dimer. Now, the answer is, aluminum chloride is an electron deficient compound with 6 electrons in the valence shell of aluminum. So, it becomes stable by forming a dimer. And I am going to show the structure, the dimeric structure of aluminum chloride. Al Now, if you count, there are it's a dimer, that is AlCl3. We have 6 chlorine and 2 aluminium. So, this is the structure of the aluminum chloride when it exists as a dimer. Now, the next question is, BCl3 does not exist as a dimer. We know that BCl3 is also an electron deficient compound, but it does not exist as dimer. Now, the answer is, due to small size of boron, it is unable to accommodate more halogen atoms around it. So, it cannot exist as a dimer. So, how does this BCl3 attain stability? We know that BCl3 is also an electron deficient species. Now, how does BCl3 attain stability? Now, BCl3 will attain stability by combining with ammonia. And we know in ammonia we have a lone pair on nitrogen atom which can be donated to boron. Okay, so we get an addition product, and I will show that reaction of BCl3 with ammonia. BCl3 trigonal planar structure plus ammonia with a pyramidal shape and a lone pair on nitrogen, and this lone pair will be given sharing as well as donation, means a coordinate bond is formed to BCl3. Now, when you show the structure of the addition product, this arrow denotes ammonia is forming a coordinate bond with boron, and this is the addition product. Addition product. Okay, so now here you have studied the term Lewis acid. Lewis acid means they are accept electrons. So, we can say here the Lewis acid is BCl3 because BCl3 accepts electron. Now, we have Lewis base here which is our ammonia because they donate electrons. Or what are Lewis bases? They are electron donors. Electron pair donors are Lewis base, electron pair acceptors are Lewis acid. So here BCl3 is a Lewis acid, whereas ammonia is a Lewis base. Now next let us discuss about the oxides of group 13 elements. Oxides. Oxides. Now they form oxides like B2O3, then Al2O3, Ga2O3, In2O3 and Tl2O3. These are the oxides formed, out of which this B2O3 is acidic in nature, Al2O3 and Ga2O3 both are amphoteric in nature, and indium oxide and thallium oxide, these two are basic in nature. Okay, now we have a question. B2O3 is acidic, whereas oxides of thallium and indium are basic in nature. Why? We know that boron is a non-metal and non-metal forms acidic oxides. So B2O3 is acidic in nature, whereas thallium and indium, they are metals and metals form basic oxides. Now the next question, write reactions to justify the amphoteric nature of aluminium. Now we discussed that aluminum oxide and gallium oxide are amphoteric in nature. So amphoteric means they can react with acid or base. When they react with acid, they act like a base. When they react with base, they act like an acid. So the question is to write reactions to justify the amphoteric nature of aluminium. So we have two examples to prove the amphoteric nature of aluminium. The first example is aluminium plus hydrochloric acid. So here aluminium acts as a base because it's reacting with acid. Now the product formed is aluminium chloride plus hydrogen gas. Now the next reaction is aluminium plus sodium hydroxide. Here sodium hydroxide is a base, so aluminium will act as acid plus 6H2O. The product formed is NaAlOH 4 times minus plus hydrogen gas. So these are the examples to prove the amphoteric nature of aluminium. Aluminium can react with acid as well as with a base. Now next is a question, white fumes appear around the bottle of anhydrous aluminium chloride. So when you check in the lab, anhydrous aluminium chloride, the neck of the bottle, when you check, you can observe white fumes coming. Now the answer is, in presence of moisture, anhydrous aluminium chloride is hydrolyzed to form hydrogen chloride gas. So in presence of water, aluminium chloride will form HCl gas, hydrogen chloride gas, which appears white in color, or that is seen as white fumes. Now the next question, BF3 behaves as Lewis acid. BF3 is a Lewis acid. You know why BF3 is a Lewis acid? Because it's an electron deficient compound. It accepts electron pair, so it acts as a Lewis acid. Now next question, aluminium alloys are used to make aircraft because the alloy, one of the example for the alloy of aluminium is duralumin. Duralumin is light, tough and corrosion resistant. So it's used to make aircraft. Now next question, aluminium utensils should not be kept in water overnight because aluminium reacts with water forming aluminium hydroxide. Next question, aluminium wire is used to make transmission cables because it's a good conductor of electricity. Now next question, concentrated nitric acid can be transported in aluminium containers because aluminium reacts with nitric acid to form a very thin layer of aluminium oxide on its surface, which prevents further reaction, and that reaction is aluminium 2Al plus nitric acid, aluminium reacting with nitric acid to form Al2O3 plus nitrogen dioxide plus 3H2O. So, aluminium oxide formed will act as a protective layer which prevents further reaction to take place. Now, next is give two uses of boron. Boron is used as a material for aircraft and boron fibers is used in making bulletproof vest. Next question, why boron can be used in making bulletproof vest or aircraft parts? Because boron is hard, has high melting point, low density and very low electrical conductivity. Now, the next question, anhydrous aluminum chloride is used as a catalyst. Anhydrous aluminum chloride is used as a catalyst, especially in organic reactions, because aluminum chloride is an electron deficient species, that is only 6 electrons in the valence shell. So, they act as a Lewis acid and can be used as a catalyst. Now, the next question is give two uses of boric acid. Boric acid is a compound of boron, boric acid, and the formula of boric acid is H3BO3. Now, two uses of boric acid is it's used as an antiseptic and in the manufacture of heat resistant glass. Now, the next question is name the isotope of boron used in nuclear industry. Boron 10, we discussed there are two isotopes for boron, one is boron 10 and the second is boron 11. Boron 10 has high ability to absorb neutrons, so it is used as a protective shield and in control rods. Now, the last question coming from group 13 is a mixture of dilute sodium hydroxide and aluminum pieces are used to open drains. Why? Because aluminum reacts with sodium hydroxide. We already wrote the equation of aluminum with sodium hydroxide, that is a reaction to show the amphoteric nature of aluminum. So, aluminum reacts with sodium hydroxide to give hydrogen gas whose pressure can be used to open drains, and that reaction we have already written, still write it again, aluminum plus 2NaOH plus 6H2O. Now, the product formed is NaAlOH 4 times minus plus 3H2. So, this hydrogen gas produced will help to open the drain. So, these are the important properties of group 13 elements. With this, we complete the properties and uses of group 13 elements. Thank you.